So in the last video, we have talked about tokenization, how AI break text into a piece of words, how the word is getting the ID, a token ID. Both are fine. And honestly, there should be one question is right back in your head. Just a word is a number, just actually anything. Like if I tell you a cat is 284, that the number 284 doesn't tell you any meaning. A cat is an animal. It doesn't tell you that cat and dog are related. It doesn't tell you anything at all. It is just a label. So how does AI got from that list of meaningless number and actually understanding the language, knowing that happy and joyful are similar, or that the word bank means something completely different depending on the sentence? That is what we are going to figuring out today. And honestly, this journey from raw numbers to actual meaning is one of the most elegant ideas from all of the modern AI. And let's get into it. Before we get to the text, let me give you a quick introduction with image, because images are actually this part and pointing point. So you have a photo of cat. What is the photo? Really, to the computer, it is a pixel, a grid of dots, and each dot has a color, and the color is just three numbers: one red, one for green, and one for blue. So 100 by 100 image, that is 10,000 pixels, each with three values. So 30,000 numbers, that is the whole image. And here is the thing: this mapping is natural. More light means bigger number, less light means the smaller number. There is an actual relationship between the number and what it represents. The AI can work with that. It can learn that is this arrangement number of visually means cat or car or a mountain. So image to pixel, pixel to number, clean and initiative. Now text. This is where it gets more interesting, because text doesn't have that natural mapping. With text, you have words. Word become token, its ID. And we covered that in the last video. So the cat sat on the mat become something like, okay, so we have a numbers, but here is the problem. This is the reality important. These numbers are arbitrary. Good might be token 6, bad might be 22, or great might be 21. No mathematically bad and great looks like together. Good is like an outer, but the completely wrong semantically. Good and great are similar, bad opposite. The model has no way to know what. It is just sees a number and it draws completely false conclusion from the proximity of the numbers. So token ID alone, they give us an identity, but no meaning, no relationship, nothing. We need something better, and people tried a few things before they lands on a real answer. The first real attempt was one-hot encoding, and the idea was to fix that false ranking problem. Here is how it works. Say your vocabulary has 5 words: cat, dog, bird, fish, and lion. Instead of giving each word a single number, you give each word a vector, a list of values, all zeros except for one position, which is 1. So cat is 1 0 0 0 0, dog is 0 1 0 0 0, bird is 0 0 1 0 0. Now no word has higher or lower number than another. No false ranking. Every word has just different slots. Problem solved, right? Well, a kind of. But here is the issue. In this system, every single word is equal distance from every other word. Cat and dog looks just different as cat and justice. The zero sense of similarity. The dot product of any two words is always 0. Always. The model is completely blind to the fact that cat and dog are both animal. The good and great mean similar thing. In practically speaking, real vocabularies have 50,000 words and more. So every word becomes a list of 50,000 numbers with exact 1 and 49,999 words, zeros. That is incredibly wasteful, conceptually expensive, and still semantically empty. So one hot encoding fixes the ranking problem, but it creates a new problem, semantically neutrality, no meaning anywhere. Okay, next attempt. What if we look at the whole document instead of individual words? This is a bag of words. Imagine literally taking all the words in the document and throwing them into a bag. Shake it up. Now count how many times each word appears. That count vector, that's your representation. So for the cat sit on the mat, the shows up twice, cat once, sit once, and so on. And this actually works reasonably well for some tasks, like spam detection. If an email contains free, win, praise, and click, even without knowing the order, you can probably guess it is spam. The frequency patterns enough. Now people extended this diagram. Instead of the single word, you count pairs. The cat set, set on. You are capturing a little bit of local order now. And n-grams, go further. Triple, quadruple, longer sequence. But here is the honest limitation. As n gets bigger, your data gets incredibly sparse. Most n-gram combinations never appear in your training data. And you are still just counting. You lost the overall order of this. Dog bites a man bites a dog. Some word, some count. Look identical to the bag of the word model. Completely different meaning in reality. And a long-range relationship, no chance. A trigram has no idea that word in the position 2 is connected to the word in the position 15. It just counts C that far. So bag of words gives us a frequency, still no real meaning. Now here is we hit the real problem, the one that all the method completely fail at. Consider this sentence. Sarah enters the old library. She knows something was hidden behind the desk. When you read it, your brain is doing a lot. You know old is describing the library, not Sarah. You know something is probably hidden behind a bookshelf or a wall. Because of the context, library, dusty, and hidden. You are doing semantic interference. You are using meaning and context together. Now, take a word bank into the sentence. I went to a bank to deposit my check, and we sat by the river bank and watched the sunset. Same word, completely different meaning. And a bag of word model exists. Bank was time and treats them identically. It has absolutely no mechanism to distinguish this. Or he was cool about the whole thing. Is a cool, calm, a stylish, or a cold? You need a context now. A truly useful representation needs to satisfy one key principle. If you replace a word with a synonym, the meaning of the sentence shouldn't be changed much. The mathematical representation should reflect that. Happy and joyful should be treated similarly by the model. None of these methods we have seen can do that, right? Not one hot, not bag of words. So the field needed something fundamentally different, and that something is word embedding. Here's the core idea. What if instead of representing a word as a single arbitrary number or a long square list of zeros, we represent it as a dense list of numbers, where those numbers actually capture meaning? Like, what if cat was representing as we might be notice those are really similar? That's the whole point. Words with a similar meaning get similar vector. Words that are unrelated get very different vectors. The distance between vectors reflects semantically similarity. Close vectors, similar meaning. Far apart vectors, unrelated meaning. Now, here is a beautiful part. Think about it with Excel. Imagine dimension for gender, dimension for reality, and dimension for power. King, high reality, male, high power. Queen, high reality, female, high power. Man, low reality, male. Woman, low reality, female. In a real embedding space, you have hundreds of these dimensions, not manually labeled, but automatically discovered by the model during training. The model figures out which dimensions capture useful distinction. You never tell it what it actually means. It discovers them on its own. And because of this structure, you can do math on meaning. King minus man plus woman equals queen, and almost exactly. Take a Beijing minus China plus Japan. You isolate that capital city concept, and Japan, you get a Tokyo. That is not a trick, that is geometry. That's the relationship encoded in number. Okay, let me make this visual, because I think this is where it really clicks. Imagine a big space, hundreds of dimensions, but let's just think of it as 3D room for now. Every word is a point in that room, and a word with a similar meaning are clustered together. In one corner, all the animal words, cat, dog, bird, lion, close together. In the other corner, emotion words, happy, sad, hungry, and can, close together. Country name cluster, food words cluster, action words cluster. Now here is a famous example. King, queen, man, and woman. Draw a line from man to king. The direction, the arrow, represents something like reality, like being elevated to the top. Now take that exact same arrow, put it into the woman, follow the same direction. You land right into next to queen. The relationship is preserved. The geometry holds. Researchers actually visualize this. They take these high dimensional vectors and use a technique called PCA to squish them down to 2D, just so we can see them, and you literally see a cluster forming. Tense terms grouped together, number words together, cat species together. The model discovered all of this just from reading text. So how does word to vector learn these vectors? Here is the intuition. The foundational idea is this. You can understand the word by the company it keeps. If the coffee always appears near the word, like morning, hot, cup, drink, the model can learn what coffee means just from that pattern. No dictionary, no manual label, just context. Word to vector uses two approaches to do this. One is CBOW, continuous bag of words. Given the surrounding words, predicts the middle word. So if you see I drink blank in the morning, the prediction will be coffee. The context predicts the center. The second is skip gram. That's the reverse. Given a center word, predicts the surrounding context. Given coffee, predict hot, morning, cup. Both approach train in the model to get good at this prediction. As a side effect, the internal numbers the model used to represent each word start to encoding meaning. words that appear in similar context end up with similar vector. The model figures it out entirely on its own, just from patterns in the text. That is, no human level, no rule, pure statistical pattern recognition that capture real meaning. Okay, so where do embedding actually live in a modern AI model, like in ChatGPT or any transformer? Here is the flow. We give the model a sentence, it gets tokenized, broken down, and the token ID. Thus, this gets into the embedding layer. Think of this as a giant lookup table. You give it a token ID, it gives you back a vector, and this list of numbers that represent the word's meaning in the model learned semantic space. So a cat token ID 284, embedding vector is 0.2, 0.5, 0.8, 0.1. This looks up a table, and technically called embedding matrix. Has one row for every word in the vocabulary, the number of columns in the embedding dimension. So for the vocabulary of 50,000 words and embedding size of 512, you have a matrix of 50,000 by 500 numbers. Every row is a word, every column is learned dimensions. And importantly, unlike word to vector, which is often pre-trained separately, in a transformer, this embedding layer is trained end-to-end. The whole model learned together, optimizing for the actual task. This embedding layer is very first thing that happens in the transformer. Token become vector, then it is real processing began. But we have one more problem. A transformer processes all the tokens at the same time in parallel, not one by one, left to right, all at once, which means it has no idea what order the word comes in. Dog beats man, man beats dog. The same embedding, the same everything. The model literally cannot tell you them apart. And order matters enormously in language models. Obviously. So before feeding the embedding into the model, we add something called positional encoding. Here is how it works. For every token, you generate a separate positional vector, a list of numbers that encode where the sequence this token sits, position 1, position 2, position 3, or position 7, whatever it is. Then you add this positional vector directly to the word embedding vector. Now here is the thing. And this addition doesn't change the size of anything. The dimension stays the same. You are just adjusting the value. The meaning and the position are now blended together in a single vector. So cat in the position 1 looks slightly different from cat in the position 7. Same word, different position, different final vector. The model can now distinguish them. Word meaning plus position combined to one vector. That is what actually gets into the transformer. Okay, let us zoom all the way out. We started with a core problem. Words are not numbers, and AI needs numbers. First, we tried token ID. Simple, but they implied false relationship. Then one-hot encoding solved the ranking problem, but created a semantic neutrality. Every word equally unrelated to other word. Then bag of word. Frequency is useful, but order disappears and the meaning is still missing. Then finally embedding. Word become a dense vector. Similar meaning sits closer together in the space. Suddenly, the model can do something remarkable. It can reason about relationship. King minus man plus woman equals queen. Beijing minus China plus Japan equals Tokyo. Meaning, genuine semantic meaning. Encoding the geometry and distance and directions in a mathematical space. And in transformer, those embeddings get positional information blended in. So the model knows not just what each word means, but it knows where it sits in the sentence. That is the foundation. That is how AI moves from raw symbol to something that starts resemble understanding. But I wanted to leave you with this. Standard embeddings are still static. The word bank gets the same vector whether it's next to the river or next to the money. Meaning is global, not contextual. That gap, that's exactly what the attention mechanism solves. And that is what we are getting into the next time. So if you like this video, please just hit the like button. That genuinely helps the channel grow. And make sure that subscribe, get the next video that we're going to see attention mechanism. And thank you for watching. See you in the next.